So graph theory is a very useful tool, especially in many situations, especially in computer science, I think. But this graph, this terminology, you have heard of this many times. Sometimes it means other things. So we will compare this with something we learned in calculus. In calculus, what does a graph mean? The graph of a function like y equals x squared means the set of points in this xy plane satisfying that relation. So like this parabola. So we say that this is the graph of this function y equals f of x, right? But in our class, graph means not this. In graph theory, a graph is kind of an abstract object. Is an abstract object consisting of vertices and edges. And many situations can be interpreted in terms of graphs. So for instance, the relation among friends. So let's say friendship among friends. So think of Facebook friends. You know, if two of you are like friends, then so in this case, vertices will be people. So vertices are kind of separated object like dot, and edges will be an edge connects two dots or two vertices, and edges correspond to okay, let's say edge is always between two vertices, so edge between two vertices A, B, like this, if A, B are friends each other. So for instance, suppose we have 4 people like this, A, B, C, D, each alphabet or vertex represents a person. And let's say B and C are friends each other, and like this. This is one situation where A, B are not friends, A, D, A, E are friends, things like that. Many situations can be understood like this. The kind of relations can be understood as graphs. We did that. So I'm going to now give you a precise definition of a graph. But you should always think of graphs something like this, where we connect dots. So a graph denoted by G, and usually we denote G as a pair of two sets V and E. A graph is, let's say this way, graph consists of two sets, a set V of vertices and a set E of edges. But we have some conditions. What are the edges? So an edge is kind of a pair of two things, two vertices. Each element in the edge set, meaning each edge, is an unordered pair of vertices. Like, for example, if G is V comma E, and I'm using the previous example that I drew. We have three A, B, C, D, E. 5 vertices, and edge is, like here, A and E, they form an edge, so we have a pair AE. And let me just write them down. CD, DE, BD. So it's like a set of elements, and each element is a pair of two or a pair of vertices. Here I said unordered. Here unordered means we don't really care the order of the two elements in a pair. Unordered means xy is considered to be the same as yx. So we don't really distinguish between b comma d and d comma b because unordered. They don't really have order there. So sometimes we write an edge like x comma y as like sometimes we will write as a set of two elements because in a set we don't really care for their order, or sometimes like x y, or sometimes x y like that. But mainly we will use this because it's the way it is written in the textbook. But unordered means we don't really worry about the order, x comma y or y comma x. We don't care. But sometimes we want to consider the order as well, because sometimes the relation between A and B are not symmetrical. Right? Oh yeah, more. By the way, because this is the first time that we learn graph theory, today we will introduce many terminologies, so there will be many definitions today. If E is an edge between two vertices U and V, then we say that. By the way, in this case, we represent these vertices and edges like this. It's common to draw a diagram like this. We have two dots labeled U and V, each vertex here, and E like this. E is an edge. This means E is an edge between U and V. We say that U and V are adjacent if they are connected by an edge like this, adjacent. Or sometimes we say that V is a neighbor of U, or neighbor of each other. And we say that U, V are incident with E. Okay, so vertex is incident with an edge. If an edge, a vertex is one of the endpoints of this edge. Okay, so mainly we will consider a graph like this, unordered. But sometimes we want to consider the order as well. So in that case, we will consider what's called directed graphs. Any question? So right here, like this is kind of abstract, so maybe it's a little difficult to understand. But if you look at more and more examples, then it should be clear what graphs mean. Another one, like sometimes you want to consider ordered pair. In that case, we will say directed graph. Directed graph, or simply we say digraph for short. Again, it's a graph consisting of vertices and edges. A directed graph consists of vertices, and let's say a vertex set, V, and an edge set E, and we have to have some conditions such that every element E in this edge set is an ordered pair now. It's ordered pair of vertices. So previously we had unordered pair, but now ordered pair. So for instance, if E is like UV, ordered means this is different from V comma U. Okay? And we really care about their order. So in this case, the common way to represent this situation is to use an arrow. So like this. So E, because we have some kind of direction where U is the first one and this is the second one, so it's nice. It'll be natural to use an arrow like this. So directed graphs, we represent edges using arrows. But for just graphs, we use just segments or curves. So example, a graph may look like this. A directed graph may look like this. 1, 2, 3, 4, 5, 6, like this. So if I draw a diagram like this, then yeah, this is. Actually, it's also possible that they may be the same. So maybe we may have something like that, or even we have the same edges, multiple edges, or parallel edges. It is possible. So let me write this over here. It is. We allow to have loops and parallel edges. Loops mean a vertex, an edge, like U comma U. Maybe directed or not. Or we may have more than one edge between two vertices, like U, V. Maybe we have many things like. Okay? But mostly we will consider graphs without loops and parallel edges. Such a graph is called a simple graph. So, definition, a simple graph. But usually when I say it's graph, it means simple graph. A simple graph is a graph without loops and parallel edges. For example, we have a graph like this. So I'm representing the vertices using dots like this, and edges using segment. This is simple, right? We don't have any loops or multiple edges or parallel edges. Parallel edges are also called multiple edges sometimes. But this one, on the other hand, is not simple because we have parallel edges like this. Not simple. Also, like if you have something like this, it's not simple because we have a loop. Simple graphs we will consider mostly simple graphs, but sometimes, if necessary, we will consider non-simple graphs. But whenever I use non-simple graphs, I will specify that. But any question? Okay. Okay, let me use the next page. Another important class of graphs is a bipartite graph. A graph G, V, comma E. This is called bipartite. If we can separate the vertices into two groups so that edges are always between different groups. From edges always connecting vertices from different groups. In other words, there are subset, say A and B, subsets of the vertex set such that they don't have anything in common. Their union is the same, is the whole set V. And every E edge is an edge UV where U is in one set and V is in another set. In other words, you don't have an edge between two vertices from the same set. Okay? So let me tell you an example. So in other words, like you have A and B like that, and vertices are something like vertices like that, and edges are always connecting two dots like this. You don't have an edge like this. This is not allowed, or this not allowed. If you can find two sets like this, then it's called a bipartite graph. So let me show you some examples. 1, 2, 3, 4, 5. Suppose that our graph looks like this. Is this bipartite? Can you divide this into two groups, two sets satisfying these relations? How do you want to define A and B? Let's say this is A and this is B. That's fine. It looks like this, right? This is bipartite. Okay, if you want, then I can precisely write. This may not be unique. There are several different ways of doing this. But if there is at least one way of doing this, it's called a bipartite graph. This is bipartite. Another example, let's say we have 1, 2, 3, 4. Is this bipartite? Is this bipartite or not? If you divide these vertices into two sets like this, then we don't have this situation because we have common some edge between two elements in the same set. But can you conclude that this is not bipartite? Your choice is wrong. That's all. There is another way. This is a wrong choice. If you say this and this, if you say this is A and this is B, then that's fine. If you say A equals 1, 2, 3, B 2, 4, then you don't have any edge between two vertices from A. You don't have any edge between two vertices from B. So it's a bipartite. So it's yes. Although it may not look immediately at the first sight, but it is bipartite. What about this? Triangle. 1, 2, 3. Is this bipartite? This is not. This is an example which is not a bipartite graph. This is not bipartite. Why? Can you prove it? Suppose that it is a bipartite graph, so that we can divide the vertices into two groups like this. Yeah, we can just say one is because one must be in one of them. So let's say A contains 1. What does that mean? Can 2 be in A? You cannot have 2 here because if you have 2, this will be connected. That's not a bipartite graph. So 2 must be in the other set. We must have 2. Same for 3, because 2 is connected to 1. We cannot have 3 there, like this. But then you see 2 and 3, there is an edge between them, so it violates the condition. So you can never find such sets A and B. So it's not bipartite. Okay? Shall we see one more example? Okay, what about this? 1, 2, 3 with no edges. Is this a bipartite graph? Huh? Bipartite or not? Partition this, make this into two groups. Actually, no matter how you put the dots, it will be bipartite. Because the only condition is that you don't have edges between vertices in one set. Already we don't have anything, so it's bipartite. Yes, 1, 2, 3, that's fine. You don't have to have an edge between these. It's bipartite. This is kind of, this is not an important example, but just to make this clarify. What about this? Just one single vertex with no edge. Is this a bipartite graph? Okay, let's go back to the definition. Here, it's like partition. It's not a partition. A may be empty. A could be empty. B could be empty. Possible. We possibly have empty set for A or B. So, because I didn't say that A is not empty, or I didn't say that B is not empty. So that's fine. This is bipartite because it satisfies the conditions of the definition. Like A has 1, B has nothing. We don't have any edge between any vertices on one side. That's fine. So it's bipartite if you want, yeah. But of course, this is kind of trivial thing, so we will be mostly dealing with graphs with many edges. Because there are no edges, it's always bipartite trivially. Any question? Okay, oftentimes we will use the following two notation. K sub n, this is called, this is the complete graph on n vertices. Meaning, like vertices 1, 2, 3 up to n, say. Complete means any two vertices are connected by an edge. So K1 is just a single dot. K2, we have two vertices, 1, 2, and they're connected. What is K3? We have 1, 2, 3. They are connected each other. What is K4? We have 4 vertices, 1, 2, 3, 4, and every two of them are connected like this. K5? 1, 2, 3, 4, 5. Then any two of them are connected like that. It goes on like this. Many things. This will be used often, complete graph. There is also a graph called complete bipartite graph. K sub n comma m is the complete bipartite graph on a vertex set which is partitioned into two. By the way, this means disjoint union. When I write like A union dot B, this means disjoint union. This means maybe it's V. This means V is the union of AB, and AB are disjoint. So sometimes this is called disjoint union because it takes time to write this always, and because it is used often, we use this quite often. They don't do this partition into two things, where we have cardinalities of the first set is n, like this. Second set is like m. Bipartite. So k, what is k? 1, 3. We have 3 points, 1 vertex on one side, 3 vertices on the other side, and they are bipartite graph. That means edges are always between one vertex from one side and another vertex in the other side. And complete bipartite means you have all possible edges, so you connect everything possible. This is not a vertex. What is k? 2, 4. You have 2 vertices on one side, 4 vertices other side. You connect all possible pairs of vertices, so that is bipartite. Is it clear? So k, n, n, comma m. So these are some definitions and notation. We will see more today. Okay. Let's move on. So the next section is about paths and cycles. So G is a graph. What is a path? A path from, and U, V are vertices. Okay, we can say it like this. This means U, V are vertices of G. A path from U to V, let's say W, doesn't matter, but U, W. Path of length n is a sequence. Like this: V0, E1, V1, E2, Vn minus 1, En, Vn. Where the first one, this is U, the last one is W, so it's from U to W. So we have E's here. So each EI is an edge between the two vertices, like that, Vi minus 1, Vi. I from 1 to n. So we have n edges like this, n edges. And each edge, for instance, like this, is an edge between two vertices in the sequence like this. Okay? Sometimes, it's kind of redundant because we know that this is a vertex, this is an edge between this and this. Sometimes we will simply write, this sequence as just using vertices, V0, V1, Vn. Then this should be understood that there is an edge between this and this. If a simple graph doesn't, this has enough information. If it's simple. Okay, let me show you an example. This example should make it clear. We have a graph that looks like this. Say 1, 2, 3, 4, 5, 6, 7, 8, 9, say. Let's say, so path is really like a real path. Think of these as like cities. There are 9 cities, and then 2 cities are connected by an edge, if it's possible to drive from one city to another, maybe using a highway, then maybe you can go from city 1 to city 9 using these edges. So let's say this is E1, E2, E3, E4. Then this is a path like this, and we will write this path like 1. We start from 1, and we use E1, and we go to 2, and then use E2, and we reach 4, and then using E3 we reach 6, and using, oh yeah, I forgot to write one more edge. So E3, E4, E5. Using E4 we can go to 7, and then using E5 we can go to 9. This is a path from which to which? 1, vertex 1 to 9. We will say things like that. Or sometimes we will omit the edges and simply say it's a path because it's too long, it's hard to read. So this is a path from 1 to 9. So any two adjacent elements must be connected by an edge, direct edge. Any question? Oh, by the way, it's possible that we can visit one vertex more than once. So, for instance, suppose that I go like this, and even go this way and then backwards and then things like this. This is also a path. You can use one edge more than once, and you can use one vertex more than once. Anything is possible as long as you follow the edges. It's a path. It's another path. So there are many paths, infinitely many paths from 1 to 9, because you can rotate this like forever. And okay, let's go to one more thing. 8. It's a sequence consisting of only one element, which is a vertex named 8. This is also considered as a path. From vertex 8 to 8. What is the length of this? The length is 0. Length is the number of edges you used in your path. So you didn't really use any edge here. It just stays there, so the length is 0. What is the length of this red path? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the length of this red path is 11, something like that. So when we study graph theory, we want to know the structures of this graph. So we want to know whether this has some property or not. And one of the simplest but important property of a graph is whether this graph is connected or not. So we need to define that first. But the definition is quite straightforward. A graph G is called connected if... How do you want to define this, by the way? Do you think this graph is connected? I haven't really defined this yet, but how do you want to say that something is connected? Just imagine that cities on a map. If you can go from one place to another, then we say that they are in some sense connected. Not necessarily just by a single edge, but if you can go from, for instance, in this case, because we can reach from 1 to 9 using these edges, we say 1 and 9 are connected. So it goes like that. If any two vertices, let's say for any two, any u, v, if you consider any two vertices, U and V, there is a path from U to V. If this is true for any two vertices, then we call this graph is connected. So, according to this definition, this graph is connected because no matter how you choose two vertices, say 3 and 5, you can go from 3 to 5 using the edges, right? So it's connected. This is connected graph. Let's. If it's not connected, we say that it's disconnected. So example, we have a graph that looks like this. It's not a pair of two graphs. This is one graph. The whole thing is a graph G. Is this connected? No, this is not connected. Disconnected, because you cannot find a path from 1 to 4. Yeah, you can only go to 2 or 3 from 1. You cannot go from 1 to 4 using these given edges. So disconnected. No path from 1 to 4. Okay. And whenever we introduce a new mathematical object like graphs, we want to say something is contained in something else. Like, what do we use that in that case? We use like subset, right? For sets, if a set is contained in another one, then we say that set A is a subset of B. Or if you learn like, I don't know, linear algebra, we have like subspace. Or if you learn like algebra, we say subgroups, something like that. So usually in mathematics, something that means it is kind of a part of the part of something, but it has a same structure. I mean, same object, in the same category of the object. So the precise definition goes like this. So we have a graph, a subgraph of G must be a graph. It's a graph. So let's say denote this graph by H. Because it's a graph, it has a vertex set, say V prime, edge set E prime. It is a graph, and it is a part of this, a subset, such that V is a subset of V prime is a subset of V, and E prime is a subset of, maybe they may be the same, subset of E. So that, in other words, subgraph is a graph obtained by selecting some vertices and some edges, right? So that is still a graph. Okay. Example, G, let's say G is this graph, 1, 2, 3, and 4. And there can be many subgraphs. Let's say H1 is like this, 2, 3, and 4. When I put a dot, that means this vertex is there. H1 is a subgraph of G, right? Because we took some vertices and we took some edges already from G. This is okay. H2. There are many. I'm just showing you something. Some of them. This is also a subgraph. What about this? H3. 1, 3, 4. Is this a subgraph of this? No, because this edge does not belong to G. Everything must be already here. It's not. This is yes. Subgraph, yes. No, this is not. Because this edge is not there. This is a problem. What about this? Here it is important that it is a graph. So if you say, okay, I'm gonna take this 1, 2, and 3. So I mean, you took an edge, but you didn't really took the vertex 3 here. This is not a subgraph because it's not even a graph, right? This is not even a graph. So of course it's not a subgraph. So you can take, you have some freedom to choose vertices from E. You have some freedom to choose edges from E, but it must be a graph. For instance, if you take like, okay, V prime 1, 3, no, 1, 2. So in this case, I took 1, 2 only, and then I took like 1, 2, and 2, 3. And this is not a graph, because if this is a graph, every element must be a pair of 2 elements from V prime. But 2, 3 is not a pair of 2 vertices from here. It's not a graph. It's not a subgraph. Any question? Question? There's something strange here? No. Feel free to ask me questions if you have. All right. 1, 2, 3, 4, 5. Suppose we have graph G like this. G is here. Then G is not connected, because you cannot go from 1 to 4. But it has kind of 2 pieces that are connected. Like G has 2 pieces of connected graphs, connected subgraphs. Right. So sometimes we want to say that this is subgraph of G, of course. This is subgraph of G. They're connected. Kind of 2 chunks of connected parts, right? But we need to have a precise definition for this. Can you define such object like this? How can you define this? So the definition is like this. G is a graph. It's called a connected component, or simply a component. In the textbook, I think it's written just a component. Sometimes we omit connected components. Component means this connected component. So component of G is a subgraph. Say subgraph H of G. It is like this. We have one component, another component. But we want to have everything there. We don't want to say that this is a component, because we want to have everything if it's possible to reach from one thing or another. So we define like this. Connected component is a subgraph consisting of all vertices and all edges of G that are contained in some path beginning at a vertex. Starting at a fixed vertex V. So for instance, here, so if we fix one vertex, like say 3, you consider all edges and all vertices that are contained in some path from 3. So because we have, this is a path, so we have 2 as a vertex. This is a path, so we have 3 there, and this is an edge is a path from here to here. So we must have all of this. So this is a connected component. Okay? This is not a connected component because it does not have all possible things that can be reached from 3. Is this clear? So this is a connected component, this is not. So in other words, a component can be understood as the largest subgraph. A subgraph that is connected, must be connected, and containing a given graph. Given a vertex. Okay, this may be a little difficult to understand at first, so let me give you some examples. Maybe this is not a good example, but you should think of this as the largest subgraph containing a given vertex. I will, in order to understand this completely, you need to see many examples. So let me show you some of them. Maybe this is too not a good example. So let's say 1, 2, 3, say 4, and 5, 6, 7, 8, 9. Okay, so we have a graph having 9 vertices and some edges like this. How many connected components are there? You should be able to answer this question if you understood it. So, okay, let me give you something. 2, 3, 4. Is this a connected component of this graph? No, because 1 is missing. You can still go from 2 to 1, but it's not there. So it's not. This is not. But what about this? Is this a connected component? Yes. What about this? Is this a connected component of this? Huh? This is some point that you may be a little confused. Or this. Is this a connected component of this? It has the largest possible graph containing this. Is this a connected component of this graph? Yes or no? Let's go back to the definition again. The important thing is component is a subgraph of G. Must be a subgraph. Is this a subgraph of this graph? What is a subgraph? You have only vertices and edges from this graph. You cannot create a new vertex or new edge. This is not an edge of this graph. This is not a subgraph. So this is G. That means not a component. So this is not a component. So component containing 1 is this. This is a component. Because it is a subgraph of this, connected. It is the largest possible, having the edges over here. Okay? But this is connected, is component. What about this? 5, 6, 7, and 8. Is this a connected component of this? Is this a component? No, because it's not connected. It's not connected. So it's not a component. Component so must be connected, and it is largest using those edges in the original graph. You are not allowed to add more edges because this must be a subgraph. So how many components are there here now? How many? This is a component, right? This is a component. This is a component. What about this? Is this a component? Is this graph, is this a subgraph? Yes, this is a subgraph containing one vertex with no edge. Is this connected? Yes, it's connected. If you take any two which are the same, there is a path. There is a path from 8 to 8. No, it's fine. And it's largest possible. No matter what edge or what vertex you add, that will be a disconnected graph. So it's a largest possible connected graph, connected subgraph of G containing 8. So this is connected component. This is also a component. So there are 4 components of this graph. So it's like this. You just separate the graph into connected parts, and they are the connected components. And the precise definition goes like that. Okay, one more thing. I think I already explained. This is not component because this is larger. This is still a subgraph connected, but this is larger. This is not, so it's not a component. Any question? Okay. I think I did this before. Do I have to? Oh, I see. Okay, good. Another definition. So we learned path. I told you that in a path we can visit one vertex more than once. We can just go visit a vertex again and again and again. Still a path. But sometimes we want to have a path without visiting a vertex more than once. This is called a simple path. A simple path from U to V is a path. From U to V, of course, with no repeated vertices. You don't want to visit a vertex more than once. This is called a simple path. And also a cycle. So here V, U and V, they may be the same. What is a cycle? Is a path. The starting and ending points are the same. But a path of length 0, which is just a path just staying there, we don't say that that's a cycle. So the path of non-zero length from one vertex to itself with no repeated edges. We may visit one vertex more than once, but we may not use an edge more than once. And a simple cycle is a cycle with no repeated edges, no repeated vertices either. Simple cycle is a cycle with no repeated vertices. But of course, the first and the last vertex, the starting and the ending points are always the same. So we don't consider them as repeated. So except the first and last vertices, because they're always the same. We don't say that they are repeated. So hopefully this example will be helpful. One, two, three, 4, 5, 6. Maybe with simple graph. Okay, let's see. Let's consider this. Yeah, this one. So this path, I'm omitting the edges. So 1, starting from 1, and then 3, and then 5, 4, 3, 2. This is a path, but not a simple path. Why? Because we have repeated vertices like this. 3 is repeated twice. It's not a simple path. It is a path, that's fine, but not a simple path. But what about this? 1, 3, 4, 2. So like this. 1, and then 3, and then 4, and then 2. This is good. This is a simple path. Okay? Let me erase some of these. What about cycle? Okay. Is this a cycle? 1, and then 3, and then 5, 6, 4, 3, 2, 1. Is this a cycle? Yes, because we didn't use any edge twice, the cycle. But not a simple cycle, right? Cycle. Oh, yeah. But not simple. Not simple cycle. Right? Because simple cycle means no repeated vertices, because we repeat this 3 twice. Cycle, but not a simple cycle. What is a simple cycle? It's just like 3, 5. It's really like a 3, 5, 6, 4, 3. This is a simple cycle. Yeah, 3 and 3, these may look like repeated vertices, but we don't count them as repeated because it's always returned to 3. The starting and ending points are not considered as repeated vertices. The simple cycle. The simple cycle looks like this, always looks like this. But for cycles, we may have like something like this. This may be this is kind of a, because we can visit one vertex more than once in a cycle, but not simple. But this one, for instance, let's say this is not a cycle because we use one edge more than once. Okay, the definition is like that. So the graph theory is a relatively new area in mathematics. Well, probably the first time it appeared in the history will be this famous problem called Königsberg bridge problem. Probably you have heard of this problem. So this is a city in Germany, I guess. There are some islands. This is a river, and there are some islands, like 2 islands like this, small islands like this. So these are lands, like A and B. So these are lands. This is a river, like that. And these are connected by some bridges. Like there are 1, 2, 3, 4, 5, 6, 7 bridges like that. Okay. The question is it possible to walk over each bridge exactly once? Oh, and let's say and return to the starting location. But of course, we assume that we don't really fly. Oh, okay. This is D. You know, once you reach from B to A, you cannot really go from A to D without using these bridges, right? That's assumed. Yeah, you may try. Okay, let's say we start from A, and then you can try to use every edge exactly once. You can try to do like this and this and this, and now you got stuck, right? Maybe you should try again with different strategies, but you will soon discover that it's not possible. If you try this a little bit, you'll see it seems impossible. But if it's impossible, how can we show that it's impossible? You cannot consider all possible things. Actually, it's possible to consider all possible things, but yeah, how can we show this effectively? Using graph theory, you can simplify this situation. You don't have to draw this all the time. Let's represent the land using dots and bridge as an edge. A, B, C, and D. So it's a kind of a non-simple graph. We have 2 edges between A and B. That's okay. B, D, and B and C are connected by 1 edge. C and A, C and D, like that. So we have this graph. This represents the situation here. And now in this graph, the question can be rephrased in this like so. Is there a cycle? Cycle means something that goes from one point to, and then we move around and return to itself, the original vertex. But we use one edge at most once. That's what a cycle means. But we still have this exactly once. That means, is there a cycle that uses all edges? But in the definition of a cycle, it means we use one edge at most once. So in this question, all edge means every edge, because it's assumed it's a cycle, every edge is used exactly once. Exactly once. That is kind of inside this sentence. The question is like that. Is it possible to find a cycle that uses every edge exactly once? Such a cycle is called an Euler cycle. So in other words, because cycle is a sequence of edges sharing a vertex. So that, in other words, that can be written in this way. Is it possible to draw this diagram without starting over again, right? At once, without how can I say? Without start over at a different point. So in Korean, we say this like 한붓 그리기, if you remember. So you use you want to draw this at once without starting over again from a different point. So such a cycle is called Euler cycle. Definition: an Euler cycle of a graph G. This may be some non-simple graphs like we saw before. Is a cycle that uses every edge. Let me put it this way. Uses all edges and all vertices. So, because it's a cycle already, every edge is used exactly once. For example, like I don't know. Do you think it's possible to find an Euler cycle of this graph? Can you find the cycle? And actually, yes. Let's say cycle goes like this, starting from here, and then goes like this and this and this and this, I don't know, this and this, this, vertex this and this and this, right? I returned to the starting point, and then I used every edge exactly once. I visited all vertices. It's okay to visit one vertex more than once, but you have to use every edge exactly once. So this is a Euler cycle. So Euler cycle is like that. So the question in this problem, a Königsberg bridge problem, is to find an Euler cycle of the given graph. Okay, so we defined an Euler cycle of a graph, and our question is, when do we have an Euler cycle? A cycle of a given graph. When we have a graph, given graph G, when do we have an Euler cycle? That's the question. Because we want to answer this question. Is there an Euler cycle? And if we have a nice criterion, then we can say that, yes, it is. Or yes, there is. Or yes, no, there is no. There's not. Before stating that criterion, we need to introduce definition. V is a vertex. The degree of a vertex, V, is the number of edges. Okay, let me just write this. It's a word. The number of edges incident to V. Then we denote this by and denoted DEG of V. So DEG of V means the degree of V. That is defined to be the number of edges incident to it. So in the previous example, like this, A, B, D, C, like that, then degree of A is what? Number of edges incident to A. We have 1, 2, 3, so 3 edges. Degree of B, 1, 2, 3, 4, 5. Degree of C, 1, 2, 3. degree of D 1, 2, 3. So 3 is like that. Oh, what if we have the loop? Suppose we have a loop like this. Then degree of C, we have 1, 2, 3, 4. Sometimes people define this to be 4, but we're going to define this to be 5. No. 1, 2, 3. We will count this twice, because this is kind of connected to C, and this part is also connected to C. So a loop will be counted twice. So here, loop is counted twice. This is just our convention. We will count this twice. So in other words, if you look at only this part very closely, then the degree is really the number of things going out from this vertex, right? Because loop is going to be something like this. So we count this twice. This will be helpful for our theorem. Okay? Now, theorem. If G is a graph that has an Euler cycle, what can we say? Then we can immediately say that it is connected. Otherwise, how can you have a cycle that uses all the vertices? Then it is connected, because Euler cycle means a cycle which contains all vertices, so must be connected. And moreover, every vertex has even degree. If there is an Euler cycle, has to be the degree of every vertex has to be even. Why? A proof is quite simple. The first one is connected is obvious, because you have to use all the vertices. It must be connected. I'm gonna just tell you very briefly why it should be even degree. So we use just consider just one Euler cycle, and it will use all the edges, right? Then you will visit this vertex. For the fix, just focus on one vertex and consider what's the degree of V is. What is the degree? Because it's an Euler cycle, we have just look at this Euler cycle. Then this will enter this vertex V at some point, and then it will leave, right? Whenever this cycle meets V, there will be two edges connected to V, right? We use one edge entering V, and we use another edge when we exit V. So whenever you visit this vertex, you use two edges at a time, right? Like this. And then you first visit this and then leave, and then you do something outside, and then you enter, and then leave, and then do this again until you use all the edges. But after this, you use all the edges, and that means you use all the edges incident to V. The number of edges incident to V, which is the degree, is even, right? That's the idea. That's a brief idea. Because idea is quite simple. So by this theorem, you can immediately say that there is no Euler cycle, right, for this vertex, for this graph. Because if there is, then every vertex must have even degree. The degrees are not even; they're all odd. There's no Euler cycle in this graph. So the answer to this question is that it's impossible, because there is no Euler cycle of this graph. No matter how you visit cities cleverly, you cannot really do that. Okay, this proof is like that. Any question? But this is just one part of the theorem, basically. The more interesting feature of this theorem is that the converse is also true. If this happens, then there is an Euler cycle. So let me write that in the next page. The converse of the previous theorem is also true. If G is connected and every vertex has even degree, then G has an Euler cycle. Proof is a little more difficult than the previous one, so I'm not going to prove this. But it is proved by induction on the number of edges or vertices. If you're interested, then you can read the proof in the textbook. But basically, the idea is using induction. So it is interesting that the converse is also true. So it is very easy to check whether a graph has an Euler cycle or not, because all you need to do is to look at the vertices, the degrees. If the degrees are all even, then the answer is yes. You can find the vertex of odd degree, and the answer is no. Very easy. Right? So for instance, let's see. Okay, let's go back to one of the examples here. Suppose that we don't have this Euler cycle constructed. But the question is now, is there an Euler cycle? If you want to answer this, all you need to do is to check the degrees. The degree is 2, 1, 2, 3, 4, 5, 6. This is 2, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 1, 2, 3, 4, 2. And then it is connected. Every vertex has degree even degree, so there is Euler cycle. You don't have to construct this to answer this question. All you need to do is to find the degrees. Very easy. Okay. There is the next theorem is probably one of the most well-known theorem in graph theory, I think. We have a graph. Oh, by the way, this definition where we count the loop twice, this is good in our definition because there's a loop, the degree is like counted twice, right? Still, the theorem is still true. But if you consider the degree of this, if you count this just once, then the theorem is no longer true. That's why I defined the degree of the loop is counted twice. Does that make sense? So, for instance, this has, what is the degree? Degree 2, 2, 2, and this is 1, 2, 3, 4. Every vertex has degree even degree. So there is a Euler cycle, like 1, it goes like this, Euler cycle. But if you count this 1 to the degree of this vertex, then this is going to be degree 3, then the theorem is not true. You have to say that if you define the loop differently, then you have to modify this theorem. That I don't want to do that, so that's why I defined that way. All right, now let me go back to this theorem. We have a graph, then sum over all vertices. Sum of the degrees of all vertices is equal to 2 times number of edges. Very simple theorem. Proof is also quite simple. Just if you consider what this sum means, then you can see this kind of easily. What does this mean? Let me just give you an example. Like suppose we have 3 vertices like this. Here you count 2 for this vertex, right? The degree is 2, degree is 2, degree is 2. All right? But let me distribute the number 2 so that like 1, 1, and 1, 1, and 1, 1 like that. So if the degree of a vertex is like D, if degree is D, then let's put 1s for each end of an edge connected to V. I'm going to distribute these vertices or degrees like this. Then what happens is the sum of degrees will be the sum of numbers here, right? I just redistribute these numbers. The 2 plus 2 plus 2 is, of course, 1 plus 1 plus 1 plus 1 plus 1 plus 1. I just change this into plus, plus, plus. But here, every edge looks like this, right? For this edge, we have to add 1 plus 1. For this edge, we add 1 plus 1. Because every edge contribute 1 to the degree of this vertex and the degree of this vertex. So the contribution of every edge inside this sum is going to be 2. That's basically the proof. So the sum of the degrees is equal to 2 times number of edges. Does this make sense? Is it okay? Yeah. So the basic idea is every edge contributes 2 to the sum. Like this edge contributed 2. Or maybe this is too simple example, so let me do this one more time. Like, what is the degree now of this graph? The way I did is like the degree is 3, 3, and 2. Maybe just one more, like 1. Okay. We are adding 3 plus 3 plus 3 plus 2 plus 1, right? That's the left-hand side. I'm going to split these numbers 1 to each edge, one side of the edge. So I'm going to divide these 3 into 1, 1, 1 like this. Then this will be distributed to each of these edges incident to this vertex, right? Also, I'm going to distribute these 2 into 1, 1, and distribute this 1, 1, 1, and this 1, 1, 1, and this one is like that. Obviously, the sum of these numbers will be the sum of the numbers here, which are just number ones, right? But if you look at every vertex and every edge, there are 2 numbers attached to it, right? So the number of ones here is, of course, number of edges times 2, which is, of course, 2 times this. Sum is equal to number of ones equal to 2 times E. That's the proof. It's quite simple. You just give a different ways of counting these numbers. Also, a very well-known theorem is sometimes called handshake lemma or handshake theorem. A shake theorem, I don't know. Also, another way to describe this theorem is that suppose that we have many students here. Suppose that some of you, I just give you some time so that you can have handshake with some other students here. So maybe this student did handshake with like these 4 students over here, something like that. And then I ask you, how many times did you perform handshakes? And then for each student, I add these numbers. Then that will be the sum of these degrees. And that will be 2 times the total number of handshake performed here. That's basically the reason why it's called handshake. But yeah. And there are 2 interesting corollaries of this theorem. Corollary. So yeah, maybe let's consider that handshake problem. So I ask you, how many times did you do handshakes? And then each of you tells me that your number, and then if I add all these numbers, then the number will be always even. In other words, the sum of the degrees of all vertices is even always. Why? Because it's 2 times number of edges. It's an even number. Okay? Another it is kind of equivalent. The number of vertices of odd degree is always even. Right? So you cannot find a graph with 3 vertices of odd degrees. The number of vertices of odd degree must be always even. Do you see why? Because, let me prove this. This is quite trivial, but this one maybe I can explain a little bit. This is the even, right? 2 times e, but let me say even, because it's 2 times e. Let's divide this into 2 things, like v degree odd, right? Degree even. Of course, degree is always even or odd, so we can separate this sum into 2 things. Now, you just consider parity of this sum. Because it's even, this number is even, so this is always even, right? So the sum, this plus this is even, and this is even. What does that mean? This must be even as well, because their sum is even. Even, this must be even. This can only happen when we have even terms, because we add odd numbers. You add odd numbers several times, and if the output is even, that means the number of terms is even. That means number of odd vertices is even. That's the proof. So from this, number of odd vertices of odd degree even. Okay, let me rewrite the theorem on Euler cycles that can be rewritten in this way. G has an Euler cycle if and only if, this is 2 ways, 2 directions. G is connected and what? Every vertex has even degree. In other words, number of vertices and number of vertices of odd degree equals 0. That means every vertex has even degree. So this cycle means you have to return to the starting point. But we can make this, change this a little bit so that you don't have to go back to where you started, but we still want to use all edges exactly once. So it's not a cycle now, it's a path. It's called the Euler path. So the difference between Euler cycle and Euler path is that in an Euler path, the starting and the ending points are different, but still you use all the edges exactly once. G on Euler path is a path from U to V. So starting and ending points are different. That contains all edges, let's say all vertices first, and uses every edge exactly once. And theorem, we have a similar theorem like this. Theorem is quite similar. G has an Euler path if and only if we write this like IFF. G is connected, of course, and number of vertices of odd degree is 2. There are exactly 2 vertices of odd degree. Then there is an Euler path. Example. We have a graph with 5 vertices, A, B, C, D, E, like that. And the question is there an Euler path? All you need to do is to compute the degrees. What is the degree of A? 2. B, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3. So there are 2 vertices of odd degree. Exactly 2. It's connected. Exactly 2 vertices of odd degree. There is an Euler path. And the 2 vertices of odd degree must be the starting and ending point. So let's find such a path. So we have to start from D. Otherwise, you cannot find the path. And then try to visit and use all vertices exactly once. Like this is one thing, right? I started from here. Okay, let me draw this again. Like that. Then you start from here and then end it there. This is an Euler path.